What we have here is a single planet orbiting a single star. The planet is kept in orbit by the gravitational attraction between the Sun and the planet. That force points from roughly the center of each object to the center of the other object, no matter where the planet is in its orbit. This is a radial force. Since it is a force like any other force, and that forces are vectors, we can impose a grid on this and add forces together. We could have a third object added to the system, a moon that is orbiting the planet. If the moon is small enough, its effects on the orbit of the planet will be very tiny when compared to the effect of the orbit of the planet by the Sun. Let's take a look at the gravitational attraction between the planet and its star, and then we will look at the gravitational attraction of things inside the planet and account for the fact that the planet is not a point particle, as almost looks in our diagram here, but is actually an extended object with a size and subparticles of its own. In this chapter, we will be looking at gravitation and orbits. Corresponding textbook is 8th edition of Halliday, Resnick, and Walker, Fundamentals of Physics. We'll be looking at chapter 13. We will not be including Einstein, no relativity yet. We'll get there later. We're going to start by looking at Newton's law of universal gravitation. First, we'll look at outside planets, and that will be the bulk of this video, and then inside planets, which will probably be the next video since it includes more mathematical considerations, especially calculus. Then we will look at orbits. The second 2/3 of this chapter is focused on orbits, the energies in orbit, and the forces on objects in orbit, as well as leaving orbit. And then Kepler's 3 laws of planetary motion, what those 3 laws are, where they came from, how did he obtain them, and how do these 3 laws connect back to Newton's law of universal gravitation. So Newton's law of universal gravitation, remember that in science, anytime you see the word law, this simply means we have an equation for it. Here's the equation that Newton started to develop. Let's discuss each piece of this equation. First off, that minus sign. Minus sign means attractive. The 2 separate objects, and here I have one planetary body and another planetary body. Those 2 objects, and we will call this guy having mass m and that guy having mass little m, simply to distinguish them. Those 2 masses attract each other, and it doesn't matter how big these 2 masses are, nor how far apart they are. There is a force of attraction between them, and it lies, this r hat means that it lies on the radial line that is connecting their centers. So the force is going to lie on the radial line, and it will point towards each of them. Also of note, since both masses are in here, we can exchange them. If I'm standing on this planet and looking at the moon, or if I'm standing on the moon and looking at the planet, it's going to be the same force in magnitude, simply opposite in direction since I've changed my point of view. And you can see I missed slightly the radial line connecting these guys. Third thing of note, is this r squared. This has a name. It's called the inverse square. As the distance between these planetary objects increases, the force is going to decrease according to the square of that distance. But it's never going to go to zero, because no matter how big this number gets, it is never actually going to get to zero. It will approach zero, but it will never actually get to zero. If we were to make a graph of this force, where we have the force on the y-axis and the position on the x-axis, first we would need to start our graph at a radius r, because we're going to deal with inside the planet later. So outside the planet, this is the equation that we use that describes the force between any object that is either standing on the surface of the planet or off the planet with a great space in between it. That force, the size of which is g, and I'll discuss that in a minute, the mass of the planet, the mass of the thing that is outside the planet, and then the distance between their centers, is going to describe an inverse square curve, which looks something like this, that will approach but never actually get to zero. Now, this mass of the planet, it could be two separate planetary bodies, or it could be a planet and it could be you. Here's a planet and here's you. You are outside the planet. Your belly button up here, which is roughly your center, is the radius of the planet plus approximately the length of your legs, another meter or so. That 1 meter is almost irrelevant compared to the 6 million meters on Earth. If you were to take the gravitational constant, the mass of the planet, the mass of you, divide by the radius of the planet, you would be calculating the force of gravitational attraction between you and the planet. We have a name for that. It's called your weight. So here's mass of you. These things describe the planet. This describes our universe. And our usual way of calculating it is mass times gravity of the planet. Now you need to keep in mind that this big G is not the same thing as little g that we summarize as just gravity. That big G is a specific number that, as far as we can tell, is the same everywhere in the universe. 6.67 times 10 to the minus 11th. And the units on that are newtons, meters squared per kilograms squared. And we can get the newtons out of this equation. We can get the units out of this equation because on the left side we will have newtons, and on the right side we'll be multiplying by kilograms squared and then dividing by meters squared. And we need to have all of the units on the right side to be working out to be newtons. Also, this doesn't have any units. This is simply a directional indicator. If we were to take big G, which is the constant of this universe, as far as we can tell everywhere in the universe, the mass of the planet that we're standing on, now the mass of Earth is approximately 5.98 times 10 to the 24th kilograms. And the radius of the Earth, which is approximately 6.38 times 10 to the 6th meters. If you were to plug those into your calculator and do 6.67 times 10 to the minus 11th, 5.98 times 10 to the 24th, divide by 6.38 times 10 to the 6th squared, you would end up with a value of approximately of 9.8. And that would be 9.8 meters per second squared. So there are a couple of different ways that we can arrive at that. We can make astronomical measurements and get these values and combine them to get 9.8. Or you can take a chunk of metal, drop it, measure that drop, and get 9.8. There are two different ways that we can verify the 9.8. The big thing, the two big things that you need to get out of this equation are the inverse square law and the fact that it is attractive. The inverse square law says the farther apart you are from the object, the less that object is going to be pulling on you. Let's take a look at a qualitative example on the next board. Suppose NASA puts a satellite in orbit around Mars. Mars has 2 moons, Deimos and Phobos. Those 2 moons will pull on the satellite in varying ways, depending on where they are in their own orbits. As I started this video, I showed the orbit of the Earth around the Sun, and then I added in the Moon, and the Moon going around the Earth. Now, if we add in more moons, or more satellites, going around the planet, that will make the gravitational calculations a bit more tricky, because they are vector addition problems. And on the next board, we'll look at a quantitative example. So, what we have here are 4 different configurations. The red dot represents the satellite, and then the 2 white dots represent the 2 moons. And what we have here in scenario A is the satellite is on one side of both moons. And the satellite is able to maintain its distance from both moons. From one moon, it's a distance small r, and then from the other moon, it's a distance big R. And it's always going to be kept in those distances from those 2 moons by its thrusters. But how much and in what direction do those thrusters need to point in order to keep the moon in this distance from each, keep the satellite in each distance from each moon, when we have the moons swirling around it essentially? So in the first scenario, they're both on the same side. In the second scenario, one moon is below and the other moon is to the right, and we've got a 90-degree angle here. In the third scenario, the satellite is now between the 2 moons. And in the fourth scenario, the one moon is a short distance to the right, and the other moon is a longer distance, big R, above. So take a look at this, think about it, and rank the magnitudes of the net force from least to greatest, and draw the net vector, the net force vector, on the satellite. So you're going to have an arrow on the red dot and pointing in the direction, roughly, this is qualitative, in the direction of the overall force. Ready, set, go. All right, if you need more time to think about this, pause the video and continue thinking. And when you've come up with your answers, then hit play. In scenario A, we have both moons on the same side. And remember, this is vector addition here. So since both moons are on the same side, they're going to be pulling in the same direction. Their pulls will be additive. And this is a line. If you compare this to all the other ones, this pull will be the greatest because they're on the same side and they're all in the same line. So if we're going to be ranking the magnitudes from least to greatest, A will be the greatest. Way over here on the right, it is bigger than everything else. Take a look at C. In C, the 2 poles are in opposite directions, so they will subtract, and they're all on the same line. So 100% of this guy subtracts 100% of that guy in a way that for B and D, it doesn't quite work out that way. So C will be the smallest. Considering B and D, what we want is the magnitudes. For B and D, where one moon is a small distance r, but that is then going to be a perpendicular distance, big R, for the other moon. The distinction between B and D is simply one of orientation. So if we take B and we rotate everything to the left by 90 degrees, or counterclockwise by 90 degrees, we will end up with D. So B and D are the same size. They are equal. What about this drawing the net force vector? All right, the net force vector, what we want is an arrow that points in the overall direction of the net force, and it should roughly represent the size of that force. This is the largest, and it's going to point to the right. The satellite is getting pulled to the right by both moons, so its thrusters are going to have to push to the left. So the net force on this guy is going to point to the right. we have a larger force from this guy and a smaller force from that guy because the one farther to the right is farther away. Consider C, in which they subtract. We have a larger force pulling to the left and a smaller force pulling to the right, and this is because of the distances. Remember the inverse square law. So the net force for C will be a small arrow that points to the left. And it points to the left because the moon on the left is much closer than the moon on the right. For B, these two vectors are going to add perpendicular to each other. And remember, the shorter distance is a bigger force. So this one will point more down, and the length of that vector needs to be shorter than the length of this vector, but longer than the length of that vector. And the same is true in scenario D, where we're going to take this vector, however long this is, and rotate it, rotating everything by 90 degrees. Let's take a look at a quantitative example in which now we have numbers. Let's put some numbers to these guys. I have a situation in which we have, let's change a couple of these numbers here. Let's have a 100-kilogram satellite, and then a 2,000-kilogram satellite, and a 1,500-kilogram satellite. And we have two distances between them, 150 meters to the right and 100 meters up. Let's calculate the net force on the 100-kilogram satellite. So calculate net force on 100-kilogram object. Let's look at the force to the right first. This force in the x direction, 150 meters is bigger than 100 meters, so that will decrease the force compared to the upward force. But this mass is bigger than the upward mass, so that will slightly increase the force. The overall force from this guy, falling on the line that connects him, will point to the right. Force X, G M over R squared. We've already accounted for the direction by saying it's going to point to the right. So we don't need the minus sign at the moment. The minus sign, remember, indicates direction and says the force between two objects is attractive. We've accounted for that. There we go. The force on this guy points to the right towards the other mass. The one mass is 2,000, the mass of interest is 100, and the distance between them is 150, and we're going to square that. This produces an overall force to the right of 5.93 times 10 to the minus 10th newtons. That's an M. And that's going to point in the x direction, which for vector notation, we give that an I hat. In the y direction, now looking at the 1,500 kilogram object, again, the force is going to be attractive between those two objects, and the net force on this guy is going to be upward along the line that connects their two centers. So we've taken care of the negative sign in Newton's law of universal gravitation equation again. Substituting numbers. into the calculator gets 1 nanonewton. Or roughly twice, if we multiplied this guy by 2, we would get pretty close to the y, the force in the y direction. What we have are two vectors here. Two vectors that happen to be very small because the masses that I've selected are not that big. So here's the force to the right. Here's the force upward. The overall force, being the hypotenuse of that triangle, we can find by the Pythagorean theorem, and then the angle we can find by doing the inverse tangent with the y force over the x force. Let's look at that. The Pythagorean theorem says take the two legs of a triangle, a right triangle, that in this case, this right triangle is a force triangle. Add the squares, and then take the square root. That will get us an overall force of 1.16 times 10 to the minus 9 newtons. That is the overall magnitude of the force. And then the angle that that force makes with a reference, and we've decided to make the reference being to the right.
Good morning. If you're parked out back by the D-Way,
59.3 degrees.
Parked in the fire lanes, we need you to move your vehicles. You're parked out back at the end of the D-Way.
So the net force we would write as
fire lane, we need you to move your vehicles.
1.16 nanonewtons, and you can write either times 10 to the minus 9th newtons or nanonewtons, they mean the same thing, at 59.3 degrees. We will pause this video here, and in the next video we will pick up looking at the force on an object that is inside another object. So if you were to take a giant drill down into the earth pretty far, and then fall down in there, what would be the effect of the force of gravity on you inside the earth as opposed to being on the outside of the earth? And we will look at, in that video, the differences between a uniformly dense planet and a non-uniformly dense planet.